Hi, my name is Rushikesh Pandarangmune, and today our topic is population modeling with ordinary differential equation. Project abstract. Population modeling is a common application of ordinary differential equation, and we will study even the linear case. We will investigate some cases of differential equation beyond the spherical case and then expand to some basic system of ordinary differential equation. The phase line and phase plane will be used assist in plotting the solution of this system uh, and constantly to aid understanding the behavior of hy- hypothetical environment over time. Now here we have one more point, a standard equation of general population growth. General population models can always be written in the form of standard equation. It looks like the following. Rate of change in quality is equal to number of births minus number of deaths, where the quantity related to the number of members of given population. Let P as to T represent the amount of the special interest present at the time T. So 2.1.1 can be written as the following. P as to T is equal to changes due to birth minus changes due to death. Suppose that represent the birth rate and D represent the death rate. Then equation is uh, equivalent to the following. P of T is equal to minus BP T dpt. The above equation can be written as following. P as to T is equal to B minus D P in bracket T. The next point is either birth rate or the death rate is a constant. Assume that death rate is a constant. Assume that death rate is a constant. Most populations are limited by the some factors for explain. It may restricted by the physical space, food, supplies, and complicate with other species, and so on. The the installab- the installability of the environment is one of the main factor that make the birth rate decreases. In order to analyze the model, find out the solution, we need to review the Vertilist equation. The logistic law of population growth is described by the first order differential equation, where n is the number of individual in population and r is the uh, intrinsic rate of changes of pollution, and k is carrying capacity of the environment. First, notice that the derivative will be 0 at n is equal to 0 and n is equal to k. Also notice that these are in fact solution to the differential equation. These two values are called these two values are called as equilibrium solution. If start with a population of 0, there is no growth and the population stays at 0. If we start with a population in the range 0 is small than n is small than k, then form our differential equation. We know that n 0 is greater than and hence n is increasing. If we start at n is equal to k, the population stays at this level. Similarly, if start with n is greater than k, then we have n as to 0 is smaller than and